Hey everyone, and welcome to this explainer. Did you know there are literally more microorganisms in a single teaspoon of healthy soil than there are people on Earth? It's wild. If you're an undergrad studying anything from ecology to data science, you might think you already know the basics about the dirt beneath your feet. But today, we're going to completely reframe that perspective. The ground we walk on is no longer just dirt, it's a high-tech frontier. It is a massive, complex matrix of data just waiting to be unlocked. We're going to explore a system that has completely revolutionized how we map our world. So get ready, because we're talking about the soil data revolution.
All right, let's dive right in. Here's what we're covering today. First, the global soil challenge. Then, enter SoilGrids. Next, the machine learning revolution. Followed by mapping in 3 dimensions. And finally, open data for everyone.
So starting with part 1, the global soil challenge, which goes way beyond just dirt. Now, you might be wondering, why is mapping the dirt beneath our feet actually a global priority? As a student looking at global systems, it's super easy to get laser focused on ocean currents, atmospheric carbon, or deforestation, right? But why should we put so much effort into mapping soil at a microscopic, granular level across the entire planet?
Well, healthy soils are literally the foundation for solving some of humanity's most pressing ecosystem challenges. We absolutely need information on world soil resources to manage climate change, basically ensuring we understand whether soils are going to help absorb environmental shocks or make them worse. It's absolutely crucial for global food production, for safeguarding our water security, preserving terrestrial biodiversity, and stopping massive soil erosion. The thing is, you can't manage what you don't measure. And honestly, until recently, our global soil measurements were incredibly fragmented.
Which brings us to section 2, enter SoilGrids, and a massive leap in resolution. To fix this huge gap between the data we needed and the data we actually had, ISRIC, World Soil Information, dropped a system called SoilGrids. And the timeline here is pretty incredible. Back in 2013, they released a proof of concept at a 1-kilometer resolution, which gave us about 30 gigabytes of data. Not bad. But then, just 3 years later, in 2016, they updated the system to a staggering 250-meter resolution, ballooning the dataset to 300 gigabytes. That is an explosive 10-fold increase in data size and precision in almost no time, which they followed up with even more system optimizations in 2019. To put that into perspective, going from 1 kilometer to 250 meters meant introducing 16 times more pixels globally. And they didn't just casually scale up the images, they fed the system way more data points and a massive stack of 158 environmental covariates. Think of these as supporting clues from satellite imagery to really boost the accuracy. This direct infusion of data resulted in a massive, game-changing jump in how well we can predict soil properties. Moving on to section 3, the machine learning revolution, or how we go from physical dirt to predictive data. So how exactly do they do it? Well, it's a pretty structured workflow. First, researchers overlay known soil observation points with those environmental covariates we just talked about to prep a regression matrix. Second, they fit spatial prediction models using machine learning. Third, they predict values at all locations across the globe. And fourth, they compare and evaluate those predictions using a rigorous 10-fold cross-validation procedure. Basically, that's just the algorithm double-checking its own homework 10 different times to make absolutely sure it's right. It's honestly amazing to see how all these diverse data streams converge. On one side, you've got national and regional soil profile databases merging together. On the other side, remote sensing data. Stuff like NASA's MODIS land products, elevation models, climate images, and lithology maps acting as our clues. All of this gets fed into an open source environment, primarily R and OSGeo tools. This is what allows machine learning to spot incredibly complex environmental relationships that a human analyst just could never, ever map manually. And the sheer scale of the inputs here is staggering. The latest iterations use over 240,000 soil profile observations worldwide and over 400 environmental covariates describing vegetation, terrain morphology, and climate. By unleashing random forest and gradient boosting algorithms, which, if you're into computer science, are essentially super advanced decision-making trees, onto this massive environmental matrix, the system spits out predictions for a 250-meter cell size across the entire planet. It is a total triumph of big data in environmental science. All right, section 4, mapping in 3 dimensions, visualizing the invisible. I absolutely love this definition from the research, Earth's epidermis. SoilGrids defines soil as the up to 2-meter thick unconsolidated material at the Earth's epidermis that is in direct contact with the atmosphere. I think it totally reframes how we think about this delicate, life-giving outer layer of our planet. It's literally a living, breathing skin, and we really need to know what's happening at every single level of it.
Because this skin is three-dimensional, SoilGrids doesn't just look at the surface. It predicts properties at 6 standard depth intervals, following the global soil map specifications, going all the way down to 200 centimeters. And at every single depth, it quantifies vital soil properties: organic carbon content, soil pH, bulk density, cation exchange capacity, which is basically the soil's ability to hold on to nutrients, and specific soil texture fractions like sand, silt, and clay. As you might guess, these subsurface properties physically shift as you move deeper into the profile. For example, soil organic carbon drops off pretty sharply the deeper you go, while bulk density actually increases. Soil pH might drift depending on the specific soil horizon. By predicting these values at very specific intervals, researchers can calculate highly accurate weighted averages for any depth interval they might need for their own specific climate or agricultural models. And finally, Section 5. Open data for everyone, and maybe your next project.
Consider this your practical cheat sheet for a future thesis or environmental modeling project. The creators of SoilGrids knew this data had to be super accessible to be useful. So if you only need to pull a spatial subset, say just your local watershed, you can easily grab that. If you need the complete global map for a massive study, you can download the entire dataset. And if you want to run cloud-based geospatial analysis without totally melting your laptop's processor, it's available right there on Google Earth Engine.
But here is the absolute best takeaway for any undergrad on a budget. There are zero paywalls here. None. SoilGrids predictions are completely available to the public under the Creative Commons CC BY 4.0 license. This facilitates widespread use, meaning ecologists, agronomists, and students all around the world can access the highest resolution global soil data ever created, completely free of charge. So I'm going to leave you with a challenge. With the Earth's epidermis mapped in 3 dimensions at a 250-meter resolution, and with the entire database sitting totally open source on the cloud, what global problem are you going to solve first? The data revolution is here, and the tools are literally right in your hands. Thanks for hanging out with me for this explainer, and keep exploring.